Okay, so linear approximations, and really that's what this ought to be called. Differentials is kind of an old way of saying, you'll see what a differential means, but really what this is about is just making linear approximations. That's it. Here, let me do one thing here. I want to get rid of that. So sometimes we call this linearization. Linearizations they're used to estimate the behavior of a function for very small changes in the input, right? So they're an easy estimation. Here's a good way to think of it. Differentials or linearizations provide a means of easily estimating a function's response to small input changes. And really all it boils down to is stuff you already know. It's just revolves around the process of taking derivatives, and you've had lots of practice taking derivatives. So that's no big deal. We're just going to write them in a slightly different form. So we're used to, this is called Leibniz Notation, which is the standard notation. dy dx is one way to write it. We know another way to write that would be f prime of x, right? And those are the derivatives you've already come to know and love throughout the year. All we're going to do when we want to use this differential approach, this linearization, is we're going to rewrite the derivative in a slightly different way. We're just going to take this original relationship and we're going to multiply each side by dx. That's it. So instead of dy dx equals f prime of x, we end up with the differential dy equals f prime of x times dx. And you can kind of think about this. We're going to practice taking some derivatives using this notation in a second, and it's no big deal. I mean, there's nothing harder or different about it, really. It's just new. Okay, here's the whole point of this thing. If we were to look at some blue function that's a curve, it's changing non-linearly. If we want to approximate what's going on close to some point point of tangency for this line here, right? Some point that's a convenient point. Say there's some value of x that's really convenient to plug into my function. Well, then it's as long as I'm staying close to the point of tangency, the linear approximation, so that linearization we call it, that tangent line to the curve, is pretty similar to the curve if I stay very close to the point of tangency. Now, if I deviate far away from the point of tangency, you can see that the line and the curve become very different, and the line wouldn't be a very good approximation anymore, right? But if I stay close to home, it is a good approximation. Okay, so this picture says a lot here. If we're saying that, well, I'll tell you what, I'm going to come back to this. Right now, I feel like that's a lot to look at. We'll come back to that in a second. So in words, delta y on this picture up here is equal to the actual change in the function, right? If you look along this blue curve, if I'm starting at some point x, and I move to the right by some amount delta x, or I could even call it dx, the function is going to change by some fixed amount, right? We could approximate that by the differential dy. It's different than delta y, right? Delta y is how much the function has actually changed from its starting value. So there's the original y value. We scoot to the right by some amount, delta x or dx, we'll call it either one. And the function's going to go up to some new value, which is just going to be whatever it is when I plug in x plus delta x into my function, right? The tangent to the curve is going to change by a different amount, but it's an approximate amount, right? It's and the whole point of this process is it's sometimes much easier to calculate how much the tangent line is changing than it is to calculate how much the curve is changing, okay? Give me thumbs on that. Is that idea just purely conceptually here? Are we on the right track with this? Does it make sense? Okay, how about questions? Any questions? Okay, we'll keep plugging ahead, and I think it'll start to become more clear here shortly. So delta y we're going to say is the actual change in the function. Dy is the change in the tangent line, right? Which is going to be our approximation to the function. And you can see here just kind of a visual representation. If I zoom in, right, if I zoom in on this point of tangency, look what happens. Like in this first graph, this increment of distance here is 0.5, but if we zoom in, now that same increment is only 0.1, and over here it's only 0.01. And you can see what happens. The curve and the tangent line are drawn together, and the tangent line becomes a better and better approximation, right? That's the whole point, the whole theory behind this process. Okay, before we dive into this too deeply here, I just want to show you how easy it is to calculate differentials. Piece of cake. Like if we start off with something like our function is y equals tangent x, then we want to calculate what the differential is. All you're going to do literally is take the derivative of tangent x and multiply it by dx. It's that simple. You guys all know that the derivative of tangent x is secant squared x. I'm just going to multiply that by the dx at the end and I'm done. That's the differential. Okay, no big deal. If I've got something like, it could be something harder. It could be some function where I need a chain rule. It doesn't matter. I'm just still going to do the same derivative I did before with chain rule. If I've got the derivative of sine squared of the quantity x cubed plus 1, think about now what are the, what's the inside function, what's the outside function, what's the next layer, and what's the next layer. Like if we're looking at this function right here, if we go back to our chain rule stuff, what's the outside layer that I'd have to differentiate first? What's being done at the outermost level to this function? Okay, so it's a sine squared, but which one comes first, the sine or the squared? It's the squared. Remember, this is kind of a tricky notation. When we write sine squared, what that really means is the quantity sine squared, okay? So first we've got hand squared is how we would have talked about it, right? And then inside, so we've got hand squared. Inside that, we've got a sine of hand. And then finally, we've got this inside piece. That's the furthest in we can go, which is the x cubed plus 1. And just a quick review of the chain rule stuff. If we were going to differentiate that, well, what's the derivative of hand squared? 2 hand, right? So there's the first layer of our chain rule, okay? And then if we look inside the next layer, what's the derivative of sine hand? Cosine hand, right? And then finally, the derivative of what's inside x cubed plus 1 is just 3x squared, right? So all I'd have to do is just, if I combine some stuff here, I could take the 3x squared and move it out front with the 2 and get a 6x squared. I've got my sine of this x cubed plus 1, cosine of that same thing. All I got to do if I want to find the differential is multiply the darn thing by dx and I'm done, okay? What about something like this? What if looks a little different. I've got a volume function, volume of a sphere. V equals 4/3 pi r cubed. If I want to calculate what dV is, well, what's the input variable? This is really V of what variable? Volume as a function of what? Radius, right? Everybody agree? I'm inputting R's and I'm outputting V's in this case. So I would be, if I differentiate this thing, I'm differentiating with respect to R, aren't I? Right? Does that make sense? So dV dr would just be, well, let's see, I've got this constant, this 4/3 pi, and I've got derivative of r cubed. I bring the 3 out front, cancels the 3, so I'm getting a 4 pi r squared, and then I'm just going to multiply that dr by the end. Instead of dV dr, it's just going to be dV equals 4 pi r squared times dr. Okay, everybody see that? Okay. Now there's more to it than just thinking of this as an algebra step, though. There's actually a little bit of physical meaning that's imparted by this process. If you think about what this means, when I use this little notation, this lowercase d notation in calculus, it means incremental, very small changes in. So really what this is telling us is something more meaningful. It's telling us that very small changes in volume are brought about by this process, by 4 pi r squared, where r is the radius, times very small incremental changes in r, right? That's how we're building these small changes in v. They're based on small changes in the radius, okay? And you could almost convince yourself that, man, the math gods are pretty clever here. This makes sense. Because if you want to think about small incremental changes in volume, there is some meaning to this. What does 4 pi r squared represent with regard to a sphere? That's something you've probably seen before. What is that? That's a formula for what? That's surface area, yeah, right? So think about that. Small changes in volume are built from whatever the surface area of the sphere is times a little additional dr. I mean, doesn't that make sense? If you think about what a sphere looks like, there's a method to the math god's madness here. There's the radius, right? So I'm just doing a cross section through this sphere. There's that represents the surface area, right? Like I took a slice through this thing, but we've got this surface area that's encompassing, it's covering the entire sphere. And then I'm just going to move this thing out by some incremental amount, dr, to make a bigger sphere, right? Doesn't it make sense in a way that I would be multiplying that surface area times the amount that I'm going to expand it to figure out what's that little extra shell of volume that I'm adding to my original volume? That's how much the volume is changing. It's changing by that shell that I just created that surrounds the original volume. You get the idea? Okay. So there really is, it really does have a little bit more meaning. We can just think about it kind of mechanistically as just a process that we do. But there really is some theory that this supports. Okay, so then if y equals f of x is some differentiable function, and delta x denotes a change in x, the differential of x, denoted as dx, is a very small version of delta x, right? We're going to move outward we're going to change x by small amounts. Then the differential of y, that's really what this means. This is how much is y changing. dy is really just equal to f prime of x, whatever the value of the derivative is at x, times dx, right? In this case, we saw it with volumes and radius, right? But it could be any output variable and input variable. The change in the output variable is equal to f prime of the value of the derivative at a convenient, at some particular value of x, times whatever the incremental little tweak in the input variable is, okay? Okay, so we're going to just by making this little notational change to differentials, to write it in differential notation, if we identify a as some convenient value of x, the actual change in the function is just going to be, it's going to be delta y. It's going to be the value of the function at a plus dx minus the starting value of the function at a, right? And we can go back to let's go back to our picture. And we can see that, right? If I want to know how much the value of the function actually changed, I'm just going to take that function value minus that function value, that y value minus that y value. That's it, right? Okay. But sometimes that's hard to calculate. Sometimes f of a plus delta x is not at all convenient to calculate. And so instead, we're going to make this approximation that the actual change in the function is approximately equal to the differential, right? And again, that differential, if we go back to this picture, the differential, that's just how much did the tangent line change, the linearization or the tangent line. How much did that change when we incrementally change the input by dx, right? What's the change in the value of the line, the height of the line? And that's very easy to calculate, That's just f prime of a times dx every time, right? Where a is the starting value and dx is how much we're tweaking the input every single time. That's it. Very, very simple. Okay? So what do they rely on? These differential approximations rely on the initial value of the input. So we've got to know what value is convenient for us to compare the value of the function to. The magnitude of the small change of the input, right? So that's what we're calling dx. If x is our, typically it's an x, doesn't always have to be an x. What is the value of the derivative evaluated at our convenient value a, but that's why we picked a, because it's easy to plug into the function and its derivative, and that's it, right? And then we're always able to really quickly calculate this differential dy. Okay, so here's a good way to look at this. This whole process of finding this linear approximation or this linearization, really all it is us just doing stuff we already know. We're just going to use the point slope formula. Here's how I like to think about this. So if I want to come up with some linear approximation, this tangent line, at some value a, right, then all I've got to do is use the point slope formula. I know that y minus some convenient y value, y minus y1 equals m times x minus x1, where x1 and y1 are values that I already know, right? When we've done this, you've done this going clear back to Algebra 1 many, many times. In fact, here, let's just do a quick example. Like, let's say we know, for example, that our line goes through the point 1, 3. And let's say that the slope, we'll go back to Algebra 1 terms. The slope is equal to 4, right? Then it's so easy for us to calculate the equation of the line. It's just going to be y minus what? Y minus 3 equals 4 times the quantity x minus 1. Boom. If we solve for y there, that's it, right? We're going to do stuff that's almost that easy, right? The only difference for us is going to be that we're going to have to calculate what the slope is by taking a derivative and evaluating a function there. And we're going to select the point of tangency based on a convenient value of x for our function. But then from there on out, it's a piece of cake. I'm just going to distribute the 4 and add the 3. And what do we get? 4x minus 4 plus 3, 4x minus 1. That would have been our linear approximation. That's the tangent line that's going to model our function for whatever application this was, right? Okay. So now let's take that idea and let's meld it with the calculus, right? So we've got this standard point slope formula. Well, what do we mean by y1? Y1 is really going to be f of a, right? A is the point of tangency. So whatever the value of the function is at a, that's going to be the y value that we know of our point, right? What is x1? Well, x1 is a, right? That's our convenient x value that we're choosing for our point of tangency. And what is m? Well, that's going to be the slope of the function at the point of tangency, right? That's the slope of the tangent line. Okay, give me thumbs. How are we doing on this idea? Okay? Okay, questions? If you can think of a question, helps you and it helps me. If there's something, put you on the spot, Lucy. You have a question? Which part of that? Is there anything that doesn't seem clear about that? Or is it just, we just need to go through some more stuff maybe? Okay. We're going to do some examples here in a second, right? That's the next step, is to actually do some examples. So then we know what we know what m is, we know what y1 is. These are just calculus. These are easily identifiable elements that make sense to us within the context of calculus, right? What is So x minus x1, x minus a, what is that? Well, that's our known value of a, and we're looking at some particular other value of x that's near a, so we could call that whole thing just delta x or dx. This is how much we're deviating from a, right? Like if a is 4, for example, and we want to know what's going on at 4.1, okay, well then that's just 4.1 minus 4. That means that dx is 0.1. We've changed our input values. We've scooted to the right from our point of tangency by 0.1. Okay, and then this whole thing right here, that looks familiar. F prime of a times dx, well, that's just the value of the differential. That's it, right? That's just the differential that we're going to practice here in a second. But that's what we calculate using the differential form of our derivatives, okay? And so we come up with the formula then. Instead of calling this y, like our new textbook uses L of x for L for linearization. So our new linear function that approximates the curve is just going to be, it's equal to L of x equals whatever the starting value of the function is at our convenient value, convenient place, plus the differential. How much did the tangent line change when we scoot to the right by a little amount? I like to remember it, instead of just writing dy, I prefer this expression right here, because this is the one we're actually going to use. When we calculate the differential dy, we do it this way, f prime of a times dx. So that's really the only formula you need. That's everything for linearizations right there. That's it. Okay? Okay, let's do an example. I'm going to skip up to an example. How about that right there? So we've got some function, some curve, f of x equals the square root of x, and we want to find a linear approximation to that curve, and we're going to embed our linear approximation around the point of tangency at 4. Why do we pick 4, do you suppose? Because it's an easy solution. What's the square root of 4? 2, right? I don't want to pick 5 because the square root of 5 is some irrational number that we're not familiar with, right? So really this is only useful to us if we're trying to find some value near 4. If we're trying to find some other value that's not close to a convenient value, we don't do this. We don't use this method, right? This is only useful when we can, we're trying to approximate something close to a convenient value, okay? So let's find the linear approximation, okay? Talk to me. What am I going to do here? If I have to start with a formula, what would that formula be? See if you can fill in the blanks here without looking at your notes. See if you can just tell me what this is. So the linear approximation formula, this is just y, right? That's the output of my line, is equal to what? F of a, good. So it's going to be the starting value of the function plus, there you go, plus my differential, right? Which is always going to be f prime of a dx. Okay, now what's our value of a here? 4, okay? So this is just equal to f of 4 plus f prime of 4 dx. Okay? And we're going to actually, like, we want to plug in a value here soon. We want to plug in a value, like we'll pick something like, here in a second, we'll pick something like 4.1 or 3.9 or something and see how well we do, okay? So I guess we know what f of x is, so it's easy for us to calculate f of 4. That's 2. But we need to know what the derivative is, so we got to calculate a derivative. What is the derivative of the square root of x? Just think of that as x to the 1/2, right? Okay, so same thing as 1 over 2 times the square root of x, right? So f prime of 4 equals what then? One-fourth, isn't it? Anybody agree? So we get an equation here, right? We come up with L of x equals 2 plus 1/4 times dx, right? And what is, if we want to just leave this as a general function, we're not going to plug in a specific value, what is dx again? Dx is just how far we've scooted away from a, right? So isn't that really just the same thing as x minus a? Those are interchangeable. So we could write this as 1/4 times dx. Well, the dx is just going to become, oops. The dx is just going to end up being x minus 4, right? Everybody agree? Okay. And if we split that fraction up, that's just giving me 2 plus x over 4 and then minus 1. Everybody see that? So my linearization, then my final answer just looks like L of x equals, well, 2 minus 1 is 1. 1 plus 1/4 x. That is my tangent line to the curve. Okay? And if I were to graph the function, it just look, will you tell me which one of those is the right graph? The right one? How come? Be the left one, wouldn't it, right? And how come? Well, because the y-intercept is 1, right? This is just mx plus b, where m is 1/4 and b is 1. Everybody agree? So it's got to be this guy here. And this is what we just did. Here's the graph of the function, and we created a linear approximation with a point of tangency at the point 4, 2. That's it, right? That's all we did. Okay? Make sense? And so if we want to calculate something like there's L of x, what if we want to calculate L of 3.9? How about? Well, all we've got to do is just plug 3.9 into our function, right? And we just get 1 plus 3.9 over 4, whatever that is, okay? 1 plus 39/40, okay? So that would be 79/40 is our, that would be our approximate value of the curve. How good is that? Well, I don't know, we could find out. I mean, we could, like they're going to ask you on the assignment, they're going to say, well, what's the percentage error, right? If you want to calculate, and it seems kind of silly in a way to do, I'm going to scoot up to a problem like that so you can just see the terminology. I got to go way up here. Like this, right? They're going to say, compute the percentage error in your approximation, which seems a little goofy because to calculate the percentage error, you actually have to calculate what the actual change in the function was. So why would you calculate the differential? I mean, in that case, you wouldn't, you know. But they're just trying to illustrate a point here that it's accurate, right? Let's try this one. Okay, why don't you guys just try this one. If you want to go to the boards and try it on the boards, like work as groups, or you can do it on paper, I don't care, whatever you want. I've got those little boards up there. But try one like this. So they're giving you a function, f of x equals 7 minus 3x squared. They're telling you that our point of tangency in this case, they're telling you it's going to be 3. and we want to estimate, use a linear approximation to estimate the value of the function at 2.9. So we'll just have some common information here. I'll let you keep working, but we're going to need f prime of x, right? So what is f prime of x here? Negative 6x. There's our derivative function, okay? And our goal here is we want to calculate what is L of 2.9. And we'll skip part B. Just A and C is really, and I guess we'll do D at the end. But A and C is what I'm interested in for now. Oh man, time flies. Hey, real quick before you go, so tomorrow I'm going to be